So the title is obviously a clickbait, so some background is necessary. So why this question came up? So the background is generating C. So, well, you say, I mean, this OCaml doesn't do a good job for me. Well, OCaml compiler is great, but unfortunately, it is of little help if I need to do, for example, if I want to have a code that, for one reason or another, runs in an environment where you cannot have OCaml runtime. Or if I want to have a code that has OpenMP directives, or if I want to have code that runs on GPU, or uses AVX instructions, or for some other reasons needs very profitable, sometimes optimizations, but generally not profitable, even sound. Well, this is the simplest example of that optimization. So in fact, we have done all of those above things, and using one of the techniques that I'm going to talk to you about. So the technique is called offshoring. So here you see OCaml code, and you can see C code. So it should be obviously that what these two pieces fragment do, right? It should also be obvious that they do the same thing, right? And it should also be obviously that, well, they're kind of almost the same, right? They have the same structure, it's slightly, different kind of, words. You can kind of think about, southern Slavic languages that had a big common core, but some languages like Slovenian use Latin alphabet, or some languages like Serbian use Cyrillic alphabet. But generally speaking, the larger common part is the same. So you can kind of think as the same thing, but to different syntaxes. Or you can think that subset of OCaml is just a different notation for C. So it's kind of, sounds funny, but it's actually very interesting that, if we can generate code in a host language, or in OCaml with some correctness guarantees, right? And which is the task of homogeneous metaprogramming. And if we can translate this generated host code into C, preserving the guarantees, and this previous thing that I showed, kind of very close correspondence between OCaml and C, it seems to be that translation should be possible, right? Then, we attain our goal that we generate C code with correctness guarantees, right? And so that was the idea of, offshoring. It's called implicitly heterogeneous metaprogramming, which was in Taha and Quarters in New Generation Computing in 2007. Right, so in a sense, that OCaml, using this offshoring, we get, heterogeneous programming out of homogeneous. And the key idea which underlies this, the generated host code, so we generate the code from OCaml, some kind of with modules, tied or function, or so forth. But the code, and this is, we can use in the generator everything that we want. But the generated code typically is, a subset of OCaml, or we can, because we control generated code, we can make it very, a very simple imperative subset of OCaml. And the offshoring only needs to deal with this subset. So offshoring is certainly not the full compilation, just, deals with this subset. So it all works great. It's a very alluring idea. It all works great, and there's only one problem. So that the underlying, the second, if the simple imperative OCaml is non-standard notation for C, it's false. And the biggest culprit is mutable variables and reference cells. And so let me tell you more about it. So here's the, OCaml expression and kind of similar looking C code expression, right? So you can think about that if we translate OCaml, if we perform offshoring translate OCaml to C, that this expression would result in this C expression. Or you can think of the other way around. If I want to generate this C expression, I should write or generate this OCaml code, right? That seems to be straightforward. It looks like, just let binding in either languages. So, but this is axis, not mutated. But what if I want to have mutated language, because mutable variables are very common in C, right? So, we all know, it's comes back from ML, then we use reference cells, right? And we can say, in order to generate this particular C code with mutation, then we have to, X has to be of reference type, ref type, and then we generate, everybody knows. So that seems to be straightforward. It's very easy to see. And the problem comes, with these expressions. It also seems to be, I mean, applying by analogy all the translations of the first two lines, then the third two lines should be also analogous. But I think you probably see that they actually have very, very different behavior, right? As always, I mean, I know aliasing, I mean, screws up everything. So, I mean, I know, C, I mean, variables are very subtle. And of course, I mean, I'm not getting in the thing that, well, we already have a problems with here, right? And I haven't, I mean, even used pointer types in C. But in C, of course, mutable cells can also be a pointer types, right? And so who knows, I mean, what kind of problems we get into there. So it's completely, I mean, I don't know, a mess. But fortunately, this mess can be salvaged if we impose restrictions. And here are the restrictions. So if there is a reference type, it has to be a base type, so int, float, and so forth. There is no, I mean, high reference. No arguments or results of reference types. And if there is a variable of reference type, that it may occur only in three contexts. So let x equal ref e, I mean, no, not any function, but just ref e, then O, I mean, the referencing or assignment. And if there is a ref e, it might only occur in this context. So it's kind of obvious, I think, by now that aliasing are precluded, right? So the thing that, I mean, spoils everything is now precluded, and I mean, it works. So these constraints are, I say, implicit in Taha New Generation Computing 2007. Why I say implicit? Actually, I mean, I have to warn you, I mean, a PR, public announcement. So if you read this paper, there is no mentioning of any restrictions. If you read the paper, then the rules that of translation that given the paper also, I mean, done in a fully general way. Only if you read the typing rules in Appendix 2 of the paper, you realize, well, actually, they are not that general, so there are actually these restrictions. So the restrictions are never stated in the paper, but they're there if you read very, very carefully. So because they're needed. So just to recap the state of the art, so if we have this particular OCaml code, so we allocate a variable of and I mean, increment it, then it's translated to C in a standard way. And this variant of the previous example with use aliasing is, well, not translatable because outside of the translation subject. So this is the state of the art. It is implemented in OCaml, and we use it for all of the things that I said on the second slide. So it works, okay? It really works. Well, as I say, more or less, it's, well, I mean, I don't know. Yeah, you sometimes become aware that there are restrictions and you have to do some kind of workarounds, and so somewhat unpleasant is. And of course, I mean, occasionally you need to have arguments of reference types in the numeric code, and you can do that. So, I mean, so in this paper, I mean, I'll show two different translations, two new translation, which is kind of improvement on the state of the art. So another, as I said, C without mutable variables, which sounds like oxymoron. How, what's the point of C of this? Well, but I mean, I know, how it works, I mean, you can see from the first example. So when we have x equal, well, ref 0 is translated as we just pick up a new variable and, well, initialize it. And x equal ref 0, it would be a pointer to that dummy variable that we introduce. And I mean, the second example, you can see each let x, OCaml example is translate of reference type, is translated a constant pointer. So one property of this translation is that the tref is translated to pointer type. So reference variables, reference types in OCaml translated to pointer types in C. So easy to trust, intuitive, right? Well, and also there is no restriction, but well, it's kind of easy to see that there are, I mean, correspondence. We have reference pointers, so we have been translate. And but the kind of drawback is that the mutable was, as it says, that without mutable variables, so we don't actually mutate variables themselves in C, right? In the generated C, I mean, access them through a pointer. So it really C kind of mirrors the OCaml pointer. And for that reason, we allocate twice as many variables, right? So we allocate Z, which is has a content, and we have X, which is also a variable, which is this piece of memory, which is a pointer to that. So there is twice as many things for, I mean, in C for one OCaml variable. So there's kind of, I mean, two kind of disappointments. And if we, I mean, I know, thinking about it deeper, then we come up with a different translation. And I explain it a little bit in detail. So if we have in OCaml, let x equal ref0, so it introduces kind of meant to be a mutable bindings, right? So it can translate it into C as a, well, mutable int x equals 0, int x equals 0, just a standard C binding. OCaml bindings over all different OCaml, all other OCaml bindings, translate it a constant C bindings. So here of the same, so here x, y is of a pointer type, of reference type, right? And so in a C, it's translated to, pointer type, but a constant binding. Then x in OCaml is uniformly translated to $x in each of every context. Then bang in OCaml is translated to C underscore. And well, you can figure out what the, an assignment is translated. Well, you can see this is kind of, ugly, star ampersand. Well, first of all, you can erase it. Star ampersand, you can, when you print it out, you erase it. But you can leave it as it is, actually the valid C. And C compiler compiles it, it would erase it for you. So that, absolutely no problem, neither performance, nor in any other cases. So again, here there's no typing restrictions. So, you can use for x and y's for any types, a high reference type or anything, reference over array references, of course. Then easy to add things like increment, and then translate it, or plus, postfix, so forth, so forth. Then, well, idiomatic C code after you erase this, star slashes, and there is no extra variables. And one of the nicest, nice places of this, features of the translation, that there's a, the translation in a sense tracks mutation. So the translation of mutable and the mutable variables, that's, well, different. And I think it's kind of nice, track mutation. So in the paper, here in the talk, I've done kind of hand waving things, but there are some formalities in the paper. So if you're interested, there is a, well, calculi, OCaml, and core C that, abstract the relevant things from two languages, and the translation is done formally. And there is also a code which has a denotational semantics of both calculi as on OCaml code. So they both translate on the same OCaml, and then there's translation with full details. And well, because translation is expressed nowadays in this implementation as a functor, then OCaml itself verifies its type preserving. And to verify that it's meaning preservation, you just need to look at the denotations in both interpret and see that actually as a OCaml code is identical. So, this one is kind of mechanical because OCaml already verified, and well, this one you have to kind of, well, if somebody's interested, can do it in Coq. So, well, the conclusions is that well, C variables are subtle, and to kind of only discover that the C is a much subtle language than appears when it tries to generate it. And so that's the interesting point is that names and the pointers are distinct, right? In C, you can access a variable using name or using pointer, but names and pointers are not the same thing. And well, I'm planning to implement it in MetaProgramming. Okay, that's it. Thank you.